For this video, I'm just going to walk you through one minor new topic here. Basically, it's going to be solving the equilibrium problems like we did previously, but there's kind of one little new idea here that you just need to be aware of. So basically, you know how to do these problems already with just one small little difference here. So sometimes what you'll see is that reactions have very small Keq values. We're talking a Keq like less than 10 to the minus fifth. So basically what that means here is if you look at Keq, we know that Keq is products over reactants. If you have a very small Keq, that means there's much more reactants present than there are products. Think about that. The only way you could get a Keq that is that small, if you're doing products over reactants, you would have to have a larger number on the bottom. So you'd have to have a larger number in the reactants. All right. So what we say here is that any change from the initial concentration of the reactants is going to be negligible, all right? And we can ignore it in our problems here, only if we're adding or subtracting that change. If we are essentially multiplying here with that change, then it can't be ignored because you're increasing it too much. But if you're adding or subtracting that change in equilibrium, it's going to be so small that basically it doesn't even matter here for the value. Sometimes it doesn't even change the value. Okay, so basically what we're saying here is when you have these really low Keq values, we can kind of ignore the change here if it's being added or subtracted, and it will make the math much easier. Okay, and I'll show you what that means here. And now this last part says you must check this assumption at the end to make sure that it's only changing by about less than 5%. I'm not going to hold you accountable for that. I'm not going to make you check the assumption. Maybe that's something you'll have to do in college. I know that I had to do that in college, but I'll show you what that looks like. But basically, what that's saying is that if the approximation was too great, you can't make the approximation because it would change your answer too much. So that's why you would need to check it. But again, I don't hold you accountable for that, but I will show you what that looks like. In order for you to see what I mean by this equilibrium approximation, we're just going to jump right in and do a problem. So this problem says determine the concentration at equilibrium for all species in the reaction below. They're giving us the Kc value, and they're giving us the initial concentration of the NOCl. All right, so the reaction is given there, and I have my ice table here set up. First thing I notice is I need to find the concentration of equilibrium for all substances here. So in my head, I'm saying, okay, this is going to be an ice table with X problem. I do have some initial values here of 0, so I don't have to worry about doing Q based on what they told me in the problem. My initial concentration of NOCl is 0.5 molar, and the NO and the Cl2 are both 0. All right, so I'm going to be forming my products here, and my reactants are going to decrease, my products are going to increase. So the products will be plus for the change, and the reactant is going to be minus. So now I can work on the change part of my ice table. Based on the stoich here and knowing that the reactants are going to be used up, I can see that the change for the NOCl is going to be minus 2x, 2 because of the 2 in front of the reactant, and minus because it's being used up. And then the NO is going to be positive 2x, all right, because of the 2 in front, and it's a product, so it's going to be forming, so it's positive. And then the Cl2 is just going to be plus x because there's only a 1 in front. All right, so now I have my change for each of these substances with respect to x here. So now I can plug in my table what the values would be at equilibrium, just doing the math here. All right, 0.5 minus 2x, and x. So now I have my concentrations in terms of x at equilibrium for all the substances. So now I'm ready to plug in to my Keq expression. So I have to write my Keq expression first. Remember, you must show that. Products over reactants here. Pay attention to the coefficients. They're going to become the exponents here with your substances. So once I write my Keq, I'm now ready to plug in. I know the value of K from the problem, and then I plug in what I know for the concentrations at equilibrium for each of the substances in the Keq expression, paying attention when I need to square it. All right, so all I did was take these equilibrium values, now plug it into my Keq expression. Now I need to work on the math here, solving this. So this is really nothing new from what we've done previously so far. This is something you should be able to do based on everything we've covered so far. Now, here is the new part. And again, like I said, this is just going to make your math easier. Since the value of Kc is really small, 10 to the minus fifth or lower here, essentially. That's what we're looking for, 10 to the minus fifth or lower. That makes the Kc very small, meaning you're going to have a large amount of reactants here, which means basically any change from the reactants is going to be very small and negligible. Right? So it's not going to contribute here to the overall concentration of the reactant at equilibrium. So what we're allowed to do here is, since this reactant is minus 2x here, we are allowed to essentially cancel that out in the problem here. Basically, it just makes our math easier. We get rid of the minus 2x part, and then we just continue solving the problem like we would. So you still have to pay attention to the squared part. That's still there. But on the bottom, you're just going to have 0.5 squared instead of 0.5 minus 2x squared. Again, this can happen because you have such a small k value, 10 to the minus fifth or lower. You're allowed to make this assumption. Basically, this change here is going to be negligible, so we can cancel it out because it's being subtracted away here. It'd be really small, and it'll make our math a lot easier. So like I said, when you start to simplify and rework this problem here, on the bottom you just have 0.5 squared. When you do your math and solve for x, you get x being 1.0 times 10 to the minus second molar. All right, so now you could check your assumption here to make sure you were justified in actually, crossing out that 2x, just to be sure here. But it's not something I hold you accountable for, but I want you to see how to do it just in case you need to do it in college. But again, we were allowed to do this approximation because our K value was so small. All right, so anytime you have a 10 to the minus fifth or lower in a problem, you can do this X approximation and make your math much easier. In order to check and see if your assumption was justified being less than 5% of the difference here, you would use this change in concentration over the initial concentration times 100. All right, again, I'm not going to make you do this, but in case you need to do this in college, this is basically what you would do. So it's the change in concentration over the initial concentration times 100, and we want that to be less than 5%. So our change in concentration here was 2x. That's essentially what we canceled out. That's what we kind of approximated in the problem. Over the initial concentration was 0.5 times 100 here. So we plug in what we got for x. When we do the math, it comes out to be 4%. So it's less than 5%. So this was valid. We were able to do this. And typically, as long as you're 10 to the minus fifth or lower, it's always pretty much going to be valid. So I'm not going to hold you accountable for doing this proving of the assumption in this class, but be aware you might need to do this in college. And this is just showing that, what you did was accurate in terms of, okay, it can be approximate, you can get rid of it, and it shows that it's not that big of a value and it wouldn't have that much of an impact on your overall number. Now that we already solved for the value of x, we do need to go back and plug in x into our equilibrium values here. So notice you do have to go back in the equilibrium row here, and you have to still do the 0.50 minus 2 times whatever x is. So even though we got rid of it in the problem for our math, make our math easier, you still need to do the actual math here. We wouldn't just get rid of this and make it 0.50. Sometimes, like I said, the change is so small with sig figs, this number may not change. But you do have to go back and actually still plug x in, and you see the concentration of NaCl did change a little bit here, but then you got to do 2x for the NO, so you get that value, and then x for the Cl2 to get that for the concentration of Cl2 at equilibrium. So we found all our concentrations at equilibrium, which is what we wanted to do, and we were able to do this X approximation because our K value was so small. You're not allowed to do this all the time. Only if you have a K value that's 10 to the minus fifth or lower, you can kind of cancel out what's being subtracted away there and make your life a little bit easier. You'll see that when we get to like acid-base problems, we will do this approximation a lot. All right, in many of the problems, we're able to do it. So it definitely does help and make your life a little bit easier here. Let's try one example here. Again, since basically there's only one new idea here, you don't need to do a ton of examples. It's basically doing the equilibrium problems as you already know how to do, with kind of making your math a little bit easier. So this example says, suppose at a temperature of 5,540 Kelvin, the Kp is equal to 3.30 times 10 to the minus 6. If you begin the reaction below with hydrogen and iodine gases at 1.23 atms and 0.798 atms respectively, what will the final pressures of the three gases be at equilibrium? All right, so the equation's already written there. I can see in this problem, I'm looking for the pressures at equilibrium. I don't know any of the pressures at equilibrium, so that's going to be a ICE table with X version of these equilibrium problems. It looks like I have the initial pressures here of the hydrogen and iodine, so I don't know anything about the HI initially, so that means it's 0. So I don't have to worry about doing Q here because one of my substances does have a starting value of 0. All right, so I'm ready to do my ICE table here. When I plug in my initial this time it's pressures, my initial pressures here, H2 is going to be 1.23 atms according to the problem. I2 is 0.798 atms, and the HI is 0 here to start. So when I look at the change, I know that the products, since they were 0 to start, they're going to be forming. So they're going to be positive for the product, negative for the reactants because they're going to be used up. It looks like we're going to lose some value of X here for H2 and I2. They're both 1 to 1, but then we're going to form positive 2X here for the HI according to the stoy. So at equilibrium, this would be 1.23 minus X ATM, 0.798 minus X ATM, and 2X ATM. All right, so now I have all my concentrations at equilibrium in terms of X. I just need to actually write the Kp expression and plug in to Kp. So when I write Kp here, remember it's going to be products over reactants. So it's going to be the pressure of Hi squared all over the pressure of H2 times the pressure of I2. All right, so we did products over reactants, wrote my Kp expression. Now I can plug in my values here. They told me that Kp was 3.30 times 10 to the minus 6, and that's going to be equal to here the pressure of Hi squared, so it's going to be 2x squared on top, all over the 1.23 minus x times 0.798 minus x on the bottom here. All right, so now when we look at this, if you pay attention here, now this is something that it's not just going to be told to you, you have to know and you have to recognize. As soon as I see that this Kp here is 10 to the minus 6th, all right, it's lower than, it's 10 to the minus 5th or lower, that means I can make this approximation. So both of these x's that are subtracted away here, we can assume that they're negligible. That makes the math much easier. On the bottom, it's just 1.23 times 0.798. All right, so when you actually do this here now and you solve for x, all right, I'm assuming you can do the math here. I'm not going to hold your hand through the math, but when you actually get to the point here and solve for x, you should find out that x is 9.00 times 10 to the minus 4th ATMs. All right, I would make sure that you can go through this problem now and solve for x. It is a little bit easier because you got to get rid of those x's on the bottom, but I would make sure you can do that. So now you still have to go back in and plug x in to your table here in order to get the values. So you'll need to do 1.23 minus x, 0.798 minus x, and then 2 times x here to get your values. So when we do this, we get the pressure of H2 being equal to 1.23 ATMs, the pressure of I2 being equal to 0.797 ATMs, and the pressure of HI being equal to 1.80 times 10 to the minus third ATMs. All right, so make sure you're going back here and plugging that value of x into your problem and getting your pressures here at equilibrium. So again, nothing really super new in these problems, just realizing that anytime you have a k value of 10 to the minus fifth or lower, you're allowed to do this approximation and get rid of the x when you're adding or subtracting here to make your math a little bit easier. But remember, once you do find x, you still got to go back and plug in that value of x for all the ones there at equilibrium. Even if you eliminate the x in the math, you still have to actually do the calculation here to determine the concentration at equilibrium. And if you notice here, this was so small, and due to sig figs, the equilibrium pressure for the H2 didn't even change. All right, and then the equilibrium pressure for the I2 only changed a little bit. All right, so this is just another equilibrium problem, but doing the x approximation when your k value is 10 to the minus fifth or lower.